This is vectors in two-dimensional reference frames. If you remember in 1D, we simply used integers, pluses and minuses, to distinguish between the directions, positive and negative. So that could be left or right, could be up or down, whatever. Because in a 1D reference frame, you only have one option to go one way or the other. So the plus and the minus are perfect for dealing with one-dimensional reference frames. In 2D, however, because you're now dealing with a planar surface, and we use the Cartesian plane as the most common model, a vector can move along the axis. Let me change colors, see it better. You could have a vector that moves along the axis. So in a sense, that's still in a linear reference frame. And you could have one that moves along this axis, also still in a linear 1D reference frame. However, when you start to move on angles, it becomes more difficult to determine the direction using pluses and minuses. This arrow here is got some positive y in it. It's got some positive y direction, but it also has some positive x direction, right? But the arrow, say down here, or over here, it has some positive y direction, but some negative x direction. And so it becomes difficult to use pluses and minuses. So for 2D, we don't do that. Instead, what we do is we use angles for direction. So the plus and minus tends to disappear. And in order to use angles, we have to decide on a common reference frame and how we'll use our angles. And I think we already talked about this a little bit, all the different ways of using angles in 2D, right? So if you have a graph and you're trying to identify an angle, you measure from the positive x-axis. So for this particular vector, you measure from the positive x-axis, and the angle is represented by theta. That's how we do it. The standard mathematical angle definition. If you have an angle, say, down in this direction, then again, the angle is still measured from the positive x-axis all the way around like that. So we have angles that can be measured this way, which are positive. You can also go the other way. Angles can be measured this way, but if you measure it this way, it's what we call a negative angle. And so there's really no point to that. It just confuses the issue and makes things more complicated. So it's better to express your angle in terms of the positive angle, counterclockwise from the x-axis. There are also other ways of doing it, as we talked about. You can assign to your reference frame a north, south, east, and west. And we already, I think, discussed how you could take a vector like this, and if you happen to know that the angle here, say, is 40 degrees, you can express that angle in a number of different ways. You can express it as north 40 degrees towards the west, right? North 40 degrees towards the west. You can also express it as west. If you think about the angle that would be here on the other side, that would be west, and of course, since it has to add to 90, it would be 50 degrees towards the north. So both of those are how we can describe the angle. You can also describe this in words as saying 40 degrees west of north. This is another way of doing it, not as common. And then you can also do 50 degrees north of west. So all these different options for using the cardinal points And of course, these could be replaced with up, down, left, and right, up, down, left, and right, any reference frame that you choose. So we've already kind of gone through that. What we want to do, though, is take a closer look at these two-dimensional vectors so we can develop a tool that's quite useful. So now I just want you to think about, well, what we're going to talk about now is resolving a vector into its x and y components. That's kind of our learning goal for this video. So we start again with a particular vector. Say we have this vector that moves like this, and we'll put in a reference frame to give us some sort of reference. Now I want you to think for a minute about scalar numbers. Scalar numbers are numbers like 2 and 7 and 5 without any direction, right? The numbers we grew up with. If you take the number 10, for instance, you can express the number 10 in many different ways. It can be expressed as 5 plus 5. It can be expressed as 7 plus 3. It can be expressed as 8 plus 2. And if you start dealing with decimals, you can express the number 10 as the sum of an infinite number of sums, couldn't you? Why would you do that? Well, you wouldn't necessarily in everyday life. But you might want to do it if these numbers, let's say 8 and 2, gave you more information about what you're talking about. So for instance, the example of having a bowl of fruit. This is a bowl, and we have 2 delicious red apples inside the bowl. And then we have 8 limes. I picked limes because green was handy. We could express the number of fruit in the bowl by saying there are 10 pieces of fruit, 10 fruit in the bowl. Or we could express this as 8 limes plus 2 apples. And this way we get a little more information about the fruit. So breaking it up into these sums gives us more information. So it's kind of a useful thing to do sometimes. Right? Okay. If I make a mistake, you guys have to tell me. Did I make a mistake? Oh, okay. You're just laughing on your own accord? Perfect. Humor is always good. Okay. What if we apply this same logic to a vector? All right? So we had our little vector up here. Let's go back to our picture of the vector right over here. And let's remember how we add vectors. To sum vectors, the sum of a vector, right? Summing vectors is done by placing them in that famous position, which we all remember, tip to tail. To the tip to tail position, which means the tip of one vector, right here, starts at where the tail of the next vector starts. And if you draw them in this position, then the sum is represented by the line from the start to the finish. Right? That's how we sum up vectors. Now, just like the number 10 can be made up of many different sums, this vector that I've drawn up above could be made up of many different vectors. As long as you start at the beginning and the vectors are tip to tail and you end at the end of the black vector, that represents a sum that would work. So this vector added to this vector equals the black vector. Right? And if you pick another sum, this vector over here added to this vector equals the black vector. It's kind of like 7 plus 3 and 5 plus 5 and 8 plus 2. There's an infinite number of vectors that I could draw that would start at this beginning, end at the end, and be positioned tip to tail. Just like there was an infinite number of sums that I could make over here for number 10. Now, why is this useful? Well, just like this was a little bit useful in the fruit, identifying the apples and limes, there are two specific vectors that are quite useful for us. So let me draw that vector again. Let's see here. Put our I'll make this a little bigger so we can work with it. And our line from here to here. There it is, Mr. Vector. There are two vectors that would tell me more about this, that could be arranged tip to tail, start at the beginning and end at the end. I'll draw them in a nice blue color. One of them is the vector that follows the x-axis. And the other one is the vector that follows the y-axis. The cool thing about these vectors is that they are at right angles to each other. So right angles is kind of critical in this case because it opens up the door for all kinds of cool math, trigonometry. There's our right angle. And they will always be at right angles, won't they? If I pick the x one in blue. So we call this guy the x component. And if we give our vector a letter name, let's just say it's vector A. Give it a little vector hat. Vector A. So this is the x component of vector A. I like to think of it as the lefty-rightiness of this vector. It's a measure of how much of this vector is lefty-righty, or back and forth. And then the other one is what we call the y component, which is a measure, the y component of vector A, which is a measure of the uppy-downy-ness. How much of this vector is uppy-downy? And we can write a simple statement. If we use this method to write it mathematically, we could say that the x component of vector A, the x part, the blue part, and if we add that to the y component of vector A, the uppy-downy part, that will equal the entire vector A. Right? Tip to tail, blue plus red equals black. The only other thing to mention is, and one of the reasons why we do this is because vectors at right angles have no effect on each other. And that's important because we want to be able to sort of break up the motion into these two different components without them having an effect on each other. Vectors at right angles have no effect on each other. You cannot make something go left by pushing up. Sorry. I think I was right. No. Effect is the noun, right? Affect is the verb. No effect on each other. So basically that means that uppy-downy, or what we could call vertical. I hesitate to use the vertical motion word because sometimes your y-axis is not representing something vertical in your reference frame. It doesn't have to. It does a lot of the time, but vertical meaning the y-axis. Uppy-downiness has no effect on lefty-rightiness. And so what that means is that we can split our vectors up into their components, their x and y components, and deal with them separately. This is what we might call the horizontal. We use that loosely. So This means that we can split up a vector into its x and y components its lefty-rightiness and uppy-downiness, and deal with them separately because they don't affect each other, which makes it easier to analyze problems in 2 dimensions. So that's basically our goal. So all we have left to do then is to figure out how we can actually get some values, some actual numbers for these x and y components. So we'll draw another picture. For some reason I keep losing that. There we go. All right, so we'll take this vector. Here's my x and y. And here's my vector going like this. Let's give this vector an amount. Let's say that this vector has an amount of 10. 10's a nice number. Maybe it's meters per second. Remember, vectors can be velocities. It could be displacement, 10 meters. But for the purpose of this demo, we'll just imagine it could be any number 10. The other part of a vector is its direction. So an important piece would be to know what the direction is. So we will define its direction as this angle on the x-axis as 30 degrees. I know my picture doesn't quite look like 30. It looks more like about 50. But we'll pick 30 because it's a nice, easy number for trigonometry, because that's where we're headed. Now we'll draw in our components. Let's draw the x component from here to here, and the y component. Notice where I stopped. I stopped directly under the arrowhead, because this has to be vertical, right? Because I have to make sure that I get a nice right angle right here. A lot of the people, when they first start doing this, they have a vector like this, and then they draw the x component, and they go too far. And then they draw the y component like this, and they say, oh yeah, well there's a right angle. But that's not the correct right angle, is it? That's not the right way. It's these guys have to be at the right angle, the red and the blue. The 2 components need to be perpendicular because x and y are perpendicular to each other. So make sure that when you're doing that, your x and y are perpendicular to each other. Okay. Let's use some trigonometry then to figure out how we can get values for these. So we'll start with the x component. If you recall, the cosine of an angle, any angle, is equal to the adjacent side divided by the hypotenuse. So I'm going to write the word adjacent right here because this is the adjacent side of my triangle. And the hypotenuse is 10. And the angle is 30. So I can extend this, or I can substitute those numbers in and write that the cosine of 30 degrees is equal to the adjacent side of my triangle, which, by the way, is the x component, right? It's what we're after, divided by 10. And if I simply multiply both sides by 10, I get this expression. 10 cosine 30 is equal to the adjacent side, which happens to be the x component that I'm looking for. That looks like I'm multiplying there, but that's just a sort of aside. Okay? So the adjacent side can be found by multiplying the hypotenuse times the cosine of the angle. Very simple. And if we do the same for the other side, the vertical component, this is what we would call the opposite side of the triangle, and we will recall that the sine of theta is equal to opposite over hypotenuse. And in this case, the sine of 30 degrees is equal to opposite side divided by 10. And so 10 sine 30 is equal to the opposite side, which happens to be my y component that I'm looking for. So I found a way to figure out the opposite side, or the y component, taking the hypotenuse, multiplying it by the sine of the angle. And these are numbers that we can figure out, right? The sine of 30 is 1/2. Whoops. Where do we go? Got lost. The sine of 30, for some reason it's not letting me go down. What's happening to our technology here? There's the fruit. We're getting closer. Maybe if I just do it on the computer, it will work better. I think it's because this little recording box is in the way. So there we are. We've reached the limit of the page. It's not going to allow us to go down any further. We will win this fight. There we go. We can calculate the numbers, right? 10 sine 30 is equal to 10 times 1/2. Sine 30 is 1/2. So this is equal to 10 times 1/2, which is 5. So we now know that the opposite side, or the y component, is equal to 5. And we can do the same for the x component. I'm a little bit nervous to try to move this down, but I will. Seems to be okay for now. If we do the same for the x component back over here, the cos of 30 is about 0.87. So this is about 10 times 0.87, and that equals 8.7. So if I go back to my triangle, I now have discovered that this is equal to 5, and this is equal to 8.7. And what's interesting here is that in vector world, 8.7 plus 5 at right angles does equal 10 at 30 degrees. Even though the two numbers, or scalar numbers, don't add up to 10. We have to remember that we're adding, and I could take this 5 and put it at a different angle and get a completely different answer. So it's all about the angles. So 5 plus 8.7 does equal 10. If the 5 and 8.7 are at 90 degrees, we'll give you the 10 at 30. All right? So that's what that means. Okay. So now that we have figured out how to find the components of a vector, we'll just do a couple of quick examples to see how simple it is. It sounds complicated, but it's not. So here is another vector, and we'll draw this in, and I'll put an arrow here, and I'll give you here, that looks like about 50 degrees. Okay? I'm going to show you something kind of interesting that happens in physics. Depending on what kind of angle you're given, whether you're using sine or cos to find your component can switch. In standard mathematics, if we always use standard angles, then the sine will always give you the y component, and cos will always give you the x component. But I've drawn one here to illustrate that sometimes you don't get a standard angle. This 50 degrees is not a standard angle. It's not measured from the positive x-axis, but it's still a useful angle. So let's draw in our components. Here's our x component. Well, let's do the y first. It's easier this time. So here's our y component, right? And notice how I'm making sure that they are at right angles to each other. There's my right angle. And if I give that vector a value, let's give it a value of 8. Then what you have to do is decide whether you're dealing with the opposite side to the angle or the adjacent side to the angle. In this case, the blue line is the opposite side of the angle, and so that means for the blue line, you write the hypotenuse, and you choose the trig ratio that goes with opposite, which is sine. So it's 8 sine 50. That's all you have to do, 50 degrees. Notice how we're using the sine function here to get the x component, because our angle is not in standard position. But that's okay, you can do that. And here, you would write 8 cos 50, and the reason being, this is the adjacent side to the angle that I'm working with. So one more example then. One more thing to point out, I guess. This 8 sine 50 is going to give you a number. It's going to give you a value. But if you look at the direction it's pointing to the left. So in your reference frame, whatever answer you get for that, can somebody maybe crunch out the value for 8 sine 50 on their calculator? And then we'll write it in. And I'll show you what we would do with that. What do you got? 6.13. Well, 6.13 tells us the magnitude of the x component. But in this particular reference frame, because it's moving left, you see how it's pointing to the left, we would use a negative 6.13 to describe that x component if we were going to use that in any formula or in any relationship or expression. So we still use the pluses and minuses, but we only use them on each of the horizontal or vertical reference frames. We don't use them for like the black vector. Now the other one, 8 cos 50, if somebody could figure out what 8 cos 50 is, what is it? 5.14. And of course, in this case, it would stay positive because it's up. Because it's up, it would remain positive 5.14. So this is the y component of the vector, and this is the x component. It's kind of like if you wanted to draw the black line on your Etch-a-Sketch, you have to turn one knob, 6.13, and the other knob, 5.14 at the same time, and what you would effectively do is you would trace out the black line. So you never actually see the red and the blue. You would only see the black line being traced out, but what you're effectively doing is moving the two knobs this much and this much to get the black line. Okay? One more quick example and I think we can wrap it up. So let's do one more. Did I just press extend the page twice? I think I did. Not that it matters. Let's go up here to another vector, and let's call it this vector here, and we'll say that this is 120. So we draw in our components. We'll give you an angle first. Let's say we happen to know this angle right here, which is going to get tight. Let's say that's an angle of 20 degrees. So we draw in our horizontal component, which would go about that far, and our vertical component, our y component. See how they're tip to tail, and they're 90 degrees. And now I can express this one. The blue one, the horizontal, is adjacent to 20, so I would choose cosine. Hypotenuse, 120, cos of 20. Very simple. No real hard calculations. And this is the opposite side for the red line, so 120 sine 20 degrees. And that's all there is to it. So next time we'll go into how we use this basic strategy to help us with projectile motion, which is two-dimensional motion.